Hello and welcome to MyScience Tutorials. In today's video, we are going to be talking about Alkoxymercuration Demercuration reaction. Before we begin, if you are new to MyScience Tutorials, kindly consider subscribing and pressing that notification button so that you don't miss any of our latest tutorials on biology, chemistry, mathematics, and physics. So let's begin. So what is an Alkoxymercuration Demercuration reaction? Now, this is one of the reactions of alkenes that yields an ether as a product. So we carry out an alkoxymercuration demercuration reaction on an alkene, and then we produce what? An ether as the product. So let's have a look at how this looks generally. So let's say we have an alkene looking like this, okay, and this carbon, we are taking this carbon as our most substituted carbon. So we add what? Mercuric acetate, which is this mercuric acetate, to this in the presence of what? An alcohol. This is our what? Mercuric acetate, and then this is our alcohol. Okay, we get an intermediate that we call the alkoxymercury intermediate. So it looks like this. We have our carbon, then we have OR attached to this, then we have this, and then we have what? Our acetylmercuric group over here. Okay, so this is the intermediate that we get when we add what? The mercuric acetate in the presence of an alcohol to an alkene. Now, when we further reduce this product or this intermediate using what? Sodium borohydride in the presence of what? A strong base such as what? Sodium hydroxide, we tend to get what? An ether which looks like this. So we have our alkoxy group at the top over here, then we have the other bonds, then we have this, then our acetylmercury group over here is replaced with what? Hydrogen, and then this is what we are calling our ether. So you can see that on the ether, or on this product that we have over here, we have the alkoxy group over here on one of the carbon, okay, and then we have the hydrogen on the second carbon we have over here. Now there are some things we need to note about this reaction. That is one, in terms of what? Stereochemistry. Okay, that is what? The orientation of attachment of what? Groups onto the carbons. This reaction is what? An anti-addition. An anti-addition. Okay, anti-addition in the sense that both the alkoxy group and then the hydrogen that we are adding cannot go to the same face of the alkene. Okay, so if the alkoxy group goes to the front side, the hydrogen has to come through the back side, because the intermediate we have over here is a bulky one and will not permit what? Our alcohol to attack this carbon through the same face, so it has to go through the other face. Now, in terms of regiochemistry, that is which groups attached to which carbon, this reaction goes by what? The Markovnikov's addition. Markovnikov's addition. That is to say, we have our alkoxy group or the OR group that we have over here attached to the most substituted carbon, and then we have our hydrogen attached to the less substituted carbon. Okay, so with this brief introduction to what an alkoxymercuration demercuration reaction is all about, let's have a look at what the mechanism or the general mechanism for this particular example that I just gave here, so that we can appreciate how we can write the mechanism of an alkoxymercuration demercuration reaction. So let's proceed. So when we have our alkene of the form this, okay, and we are using this carbon with the asterisk as our most substituted carbon, we then add what? Our mercuric acetate to it, okay, in the presence of what? An alcohol, and this will give us what? An intermediate that looks like this, with our what? Acetylc group over here, and then we further add what? Sodium borohydride in the presence of what? A base, and then we get what? Our ether as our product with the hydrogen over here. So let's look at the mechanism for this reaction. All right, so first of all, before this reaction proceed, the mercuric acetate that we have over here will dissociate to produce what? The acetosymercuric ion, and then what? The acetate anion. So we have the mercuric acetate over here, we have it over here. It will then dissociate to produce the acetosymercuric ion, and then this in solution. Okay, now mercury has a lone pair, so this also has the lone pair over here. Now after we produce this, okay, the acetosymercuric ion over here now goes to attack the alkene. So we have our alkene, then we have the acetosymercuric group over here, this, okay, with a positive charge, and then the lone pair on it attacking the alkene. Okay, now the double bond is an electron rich center, so it will be what? Attracted towards the positive charge over here, and then this lone pair will also attack one of the carbons over here to produce an intermediate that looks like this, that has what? More or less like a chain or a cyclic compound. So it looks like this, and then we have this, the mercury attached to both carbons, and then the positive charge is still on the mercury. So now that we have this intermediate, we now have our alcohol coming into the reaction. Now the alcohol, because of this, the nature of the group over here, the acetosy group over here, it will not permit the alcohol to attack through this phase. Okay, so the alcohol will have to attack through the other phase or the opposite phase for the reaction to proceed. Now remember, I said this reaction in terms of what? Regiochemistry goes by what? The Markovnikov's addition. So which means the one of the lone pairs on the alcohol over here will be used to attack the most substituted carbon. Okay, in this case we are using this carbon with the asterisk as our most substituted carbon. So the lone pair over here will attack this most substituted carbon, releasing these electrons onto the mercury, and then from here we get a product that looks like this. So we now have our alcohol over here. Okay, now this now bears a positive charge. We now have our bonds over here, then we have this, then we have what? Our acetosy group over here. All right, so now that we have this, another what? Alcohol molecule will now come to pick up a proton from this intermediate. So this picks up a proton, releasing these electrons onto this oxygen. So from here we get our intermediate that now looks like this, with our what? Acetosymercuric group over here. So this is our intermediate. Now that we have our intermediate, all that we have to do is to add what? Sodium borohydride to this. And what the sodium borohydride does is it what? Carries a reduction reaction on this intermediate just by replacing the acetosymercuric group over here with hydrogen, and then we get what? Our product as what? The ether. So we have our carbon with the OR group or the alkoxy group, then we have this, then we have the acetosy group over here or the acetosymercuric group over here replaced with hydrogen, and then this is our product that we are calling the ether because of what? The alkoxy group over here. So we can see that in terms of what? Stereochemistry, we are adding the alkoxy group to the other side or opposite side of the carbon, and then the hydrogen goes to another phase of this second carbon. And in terms of regiochemistry, we added the alkoxy groups to the most substituted carbon, and then we add the hydrogen to the less substituted carbon. Alright, so with this brief introduction to the mechanism of what? Alkoxymercuration Demercuration reaction, let's further proceed to have a look at a practical example. So the first example we want to look at is what? 1-methyl-cyclopentene. So we are using this 1-methyl-cyclopentene as our alkene. So we have this is our 1-methyl-cyclopentene, and then we are adding what? The first reagent we are adding is what? Mercuric acetate, okay, in the presence of what? Methanol, okay. Then secondly, we are adding what? Sodium borohydride, okay, in the presence of what? A base. All right, so the product that we are supposed to get is what we are to find. So we don't know the product yet, so we have to show the mechanism to how we can use this reaction, perform an alkoxymercuration demercuration on 1-methyl cyclopentene to get the product. So let's look at the mechanism. Now, because if you look at the reagent, okay, the reagent should tell you what type of reaction we are carrying over here. Now, in our previous tutorial, we also dealt with what? Oxymercuration demercuration reaction. Now, with oxymercuration demercuration reaction, the only difference between that and alkoxymercuration demercuration is what? In the first step, we add what? Mercuric acetate, okay, in the presence of what? Water. This is for what? Oxymercuration demercuration reaction, before we then proceed to add the sodium borohydride in the presence of what? A base. And this oxymercuration demercuration produces what? An alcohol as our product. Now, this we can see that we have what? An alcohol over here. So once we are not adding the what? The mercuric acetate in the presence of water, and then we are adding it in the presence of an alcohol, know that the reaction is what? An alkoxymercuration demercuration reaction, and you are not supposed to produce an alcohol but rather an ether, okay. So that is just by the way. So okay, so from here straight ahead, we know that our what? Our mercuric acetate over here is going to dissociate. So we have this with a lone pair, then OAC dissociating to produce, it dissociates in the presence of heat. I forgot to state that earlier. It dissociates in the presence of heat to produce our ions. So we have this, and this produce, okay. So once we have the acetylmercuric group produced, it now goes to attack the alkene, so, or react with the alkene. So we have the alkene here, CH3 here, then we have our acetylcy group now coming to attack, okay. So the double bond over here, okay, will attack the positive center, and then the lone pair over here will also attack one of the carbons over here to produce a product that looks like this. So we have our hydrogen here, our CH3 here, then we now have for this with this over here, okay. All right, so now that we have this, our methanol can now come and attack. So we have our methanol now coming to perform its attack. Now remember, the methanol cannot attack, okay, through the same phase, so it has to attack through what? The opposite phase, okay. So if we assume that what? The mercuric acetate over here attack through the front, it means the methanol has to attack through the back side, okay, and not just on any carbon but the most substituted carbon. Between these two carbons that initially bears the double bond, this carbon over here is the most substituted carbon because it has one alkyl group attached to it, whilst this carbon has only, no sorry, this carbon has two, let me see, 1 2 3, it has, yes, 3 alkyl groups attached to it, and this carbon only has what? 2 alkyl groups attached to it. So this is our most substituted carbon. So the alcohol will perform what? A backside attack onto this carbon over here, then breaking this bond and releasing the electrons onto the mercury group over here. So from here, this is what we get. Right, so because we performed a backside attack, we need to show what? Stereochemistry for this product. So if we put our hydrogen on a wedge over here, then it means what? Our acetylcy group also has to be on the what? On the dash over here. So we have this OAC, okay. Now the methyl and then the acetylcy group over here will have to be in the same phase. So we have this, okay. then the alcohol which performed the backside attack has to be what, on a dash over here. So we have this. Okay, then we have our oxygen here, hydrogen here, then we have what, the CH3 over here. Now it bears a positive charge. Okay, so this is the stereochemistry that we are showing over here. So we can see that the alcohol that we added is on different phase of the, it's on a different phase, and then what, the mercuric acetate group that we also added is also on what, on a different phase. So from here another alcohol molecule will just come, okay, and pick up a proton, releasing these electrons onto this oxygen. So from here we get our intermediate. So our intermediate now looks like this. So we have on the dash over here hydrogen, then on the wedge we have this. Okay, then on the other, the most substituted carbon, we have on the wedge we have the methyl group, and then on the dash, okay, we have our OCH3 group, or the alkoxy group. So this is now our intermediate. So from here we just add what, sodium borohydride in the presence of what, a base. And what this does is what, it performs reduction on the acetosymercury group over here by replacing it with what, with hydrogen. Okay, so once that is done, this is what we get as our product. So we have the hydrogen that we are adding over here, then we have our methyl group over here. Let me use another color to indicate the groups that we are now adding. So the new groups that we are adding, the hydrogen is on the dash over here, and then the alkoxy group over here is on the wedge over here, so OCH3. Okay, so this is our product. This is our product, and we can see that in terms of what, stereochemistry, it is what, an anti-addition, and in terms of what, regiochemistry, we added the alkoxy group to the most substituted carbon, and then the hydrogen to the less substituted carbon, and which is what, the Markovnikov's what, addition. All right, so let's go ahead and look at what, another example. So example number 2, we have the alkene, this as our alkene. We have CH3 here, hydrogen here, another CH3 here, another what, CH3 over here, and then we are adding what, mercuric acetate in the presence of what, ethanol, CH3 CH2 OH, and then secondly we add what, sodium borohydride. And then the product that we are going to get, we don't know, so we are to give the product, given that the intermediate that we are expected to obtain looks like this. So the question has given us the intermediate, then we have this as our intermediate, CH3 here, then we have O, CH3 CH2 here, then we have this with hydrogen here, then we have what, CH3 here, then we have on this side we have the mercury, then the OAC group attached over here. So this is 90% according to the question. Okay, so mind you, this is the intermediate and not the product. So from here, before we carry what, the reduction to get what, our product. Okay, so we have to write the mechanism of how we convert this alkene over here to this intermediate, which is what, 90% of the yield, before we perform the reduction to get a product. All right, so let's go ahead and write the mechanism for this beautiful reaction that we have. So as usual, we have our what, our mercuric acetate dissociating to produce what, the acetosymercuric ion. So I will just ignore that step or jump that step and go straight to the mechanism. So I have this CH3, then the hydrogen over here, then I have the acetosymercuric ion now attacking. Okay, so from here I know that the double bond will attack the positive center, and then this electrons will attack what, one of the carbons over here, okay, to form a cyclic compound that looks like this. So I have my CH3 here, then I have what, hydrogen here, then I have CH3 here, I have what, CH3 here, then I have this, okay, OAC over here with a positive charge. Right, so from here my ethanol will now come and perform its attack. So I have my ethanol coming, CH2O hydrogen. Okay, now the ethanol has to come and attack the most substituted carbon, because this reaction goes by what, the Markovnikov's addition. So the ethanol attacks this carbon, because this carbon is the most substituted carbon. So it attacks this carbon through the backside and expelling these electrons onto this mercuric group over here. So from here, this is what we get. So we have this with our what, CH3 over here, then we have our CH3 over here, then we have the alcohol that we are adding. I'll bring it to the bottom so that we get it as how the product is looking, because this is through the backside. Okay, so I'm having it over here, OH, then I have what, CH3 CH2 over here. So from here we have this, the carbon, then this is supposed to be at the bottom over here, but I'm just sending it to the top. It's still the same. So I have what, this over here, I have the hydrogen, and then I have the CH3 now at the bottom. Okay, so from here another what, ethanol molecule will not come and pick what, a proton from this over here. So we have this CH3 CH2O, this will now come and pick a proton, then releasing these electrons onto this oxygen over here. So from here, this is what we get. We now get our intermediate, okay, which looks like this, CH3 CH2, then we have this, we have our acetosymercuric group at the top over here, we have hydrogen, then we have what, our CH3 or the methyl group over here. So from here, all we need to do is to add what, our sodium borohydride in the presence of what, a strong base such as what, sodium hydroxide, and then the reduction will be performed by changing what, the acetosymercuric group over here with hydrogen, and then we now get our product. So this is what our product looks like. So our product will be here. So we have the carbon, this carbon with the methyl group over here, then another methyl group over here, then we now have our alkoxy group over here, CH3 CH2, then bonded to what, our hydrogen, the new hydrogen that we are adding, or the new hydrogen that we obtained from the reduction is the one at the top over here, then the other hydrogens, and then the alkene, the methyl over here. So this is our product. This is our product. So thank you so much for watching. This is how we perform what, alkoxymercuration demercuration reaction on an alkene to produce an ether. So thank you once again for watching, and I'll see you in the next video. Bye bye.